7.3 Trig equations. Find all the solutions of the trig equation 2 cosine theta minus root 3 equals 0. Solve the equation for theta when you're in the interval 0 to 2 pi by isolating cosine of theta. Alright, so to tackle this problem, first thing we're going to do is basically just get that cosine of theta isolated just like you would with any other kind of equation. So the first thing you want to do is you add root 3 on both sides. And in doing so, you get 2 cosine theta is equal to root 3. Divide both sides by 2. So you can see that cosine theta is equal to root 3 over 2. It is at this step right here that you ask yourself, whenever you get that trig function isolated, always ask yourself, okay, so now that this is isolated, when does cosine of theta give me a positive value? Cosine of theta gives me a positive value. You always want to create a mental picture here. I would really recommend you always visualize this by drawing the unit circle out. And so here we see that cosine of theta gives us a positive value in quadrant 1 and also in quadrant 4. Okay, so in doing so, we see that cosine theta, the value of root 3 over 2, if you know your unit circle values by now, hopefully you understand that the value of that would give you either pi over 6, right, in quadrant 1, or 11 pi over 6 in quadrant 4. Okay, so those are basically your two values. Now, normally we would have said, okay, let's find all the coterminal values as well, right? Because it's an infinite loop where you can just keep going around in a circle. But keep in mind that we are restricted by 0 to 2 pi, so there's no need to add plus 2 pi n to this. You simply just have these two answers because it just needs to be contained within 0 and 2 pi. Okay. If we did want to find all the general answers, if there were no restrictions, that's what B is asking us for. If there were no restrictions, then how can we find all the solutions? Well, we know that we're basically going to have the value of pi over 6, and we can add all coterminal values of 2 pi n, where n is an integer. Likewise, we can also find that 11 pi over 6 can be added to 2 pi n, where again n is an integer. So that's what you'd want to write if you want to find all the solutions. Now it says list 8 of the solutions in the next part. So if we want to list the 8 solutions, well, we've got pi over 6 plus 2 pi n, and we also have 11 pi over 6 plus 2 pi n. So, thinking about the first one, here's pi over 6, and if we add another 2 pi to that, then in a way it's like we're saying let's add, if we want a common denominator, let's add 12 pi over 6n. And so if we add 12 pi over 6n, we would get answers like pi over 6. We would get 13 pi over 6. We would get 25 pi over 6. And let's do one more. We will get 37 pi over 6. Okay, just by adding the n, where in this case, if that was not clear, this was when n is 0, n is 1, n is 2, and n is 3. Now I stopped here at 4 solutions just because I see that we need to find 8 solutions, so I figured it's basically divvying it up in half, right? We have 4 solutions for the first case. We have 4 solutions for our next case. So we have 11 pi over 6, and then from here we can add coterminal values by adding 2 pi n. So it's like saying let's do 11 pi over 6 plus again 12 pi over 6n. So if we do that, we can get values like 11 pi over 6, that's when n is 0. We would get 23 pi over 6 when n is 1. We could get 35 pi over 6 when n is 2. And we would get 47 pi over 6 when n is 3. So there we are. We have our 8 total answers there. Okay. All right, going on. Solve cosine of theta is equal to 0.42 if we're contained within the restriction of 0 to 360 degrees. Now notice this is in degree format. Also notice that the question is asking us to solve algebraically and also confirm graphically. So I actually want to work the other way around. I actually would like to show you confirming graphically what this looks like. Keep in mind what we're really looking for here. Really, this is a system of equations. It's like saying we have a function cosine theta, and we also have another function, 0.42. And we're saying, okay, if this is a system of equations, let's set them equal to each other and see when these two lines intersect. Well, cosine theta looks something like this. Right, we have our basic cosine graph, something we've learned already. And the cosine graph we know has a maximum value of 1 and a minimum value of -1. Okay, there's our fundamental cosine graph. And then if we wanted to find when this intersected the value of 0.42, well, what is 0.42? It's just a constant number, and therefore that would just be a horizontal line. The value at 0.42, here's 0.42. And so we're just kind of seeing when does that cosine graph intersect our horizontal line of 0.42. It intersects at those two locations there. Now, if you think about the parts of a cosine graph, you know that a full circle is 360 degrees. This is going to be in degree format, not radians. And so therefore we now have that at the minimum value here. We know that that's going to be 180 degrees. And we also know some other important points right here, right, where the x-intercepts are. Those are going to represent the 90-degree angles and 270-degree angle, like that. Okay, so we can see that the intersection points are actually just a little shy of 90 degrees and a little more than 270 degrees. Okay, so we're going to find those answers now as we solve it algebraically. And we are going to need a calculator because it says to round it to the nearest tenth. So keeping in mind that since cosine of theta is equal to 0.42, remember that when it comes to inverse operations, or rather, first of all, before I set up inverse operations, remember what we had just mentioned previously was when you see that your trig function is isolated, it is now isolated, this is where you want to be creating a mental picture here of where does this trig function give you a, in this case, positive value. Okay, so since this is a positive 0.42, when does cosine give you a positive value? Well, that would give us a positive value in quadrant 1 and quadrant 4. So we want to make sure we find values in quadrant 1 and quadrant 4. Okay, so in seeing how we have cosine theta equals 0.42 and our ultimate goal is to really isolate that value of theta, then what we want to do is do the inverse operation, or in this case, cosine inverse of both sides, and that's going to get rid of your cosine. And therefore on the left side, you're just left with theta. And on the right side, we have cosine inverse of 0.42. Let's go ahead and calculate that. So we have cosine inverse of 0.42. And we'll go in degree format here. And that's giving us a degree of 65.165 degrees. Let's go ahead and go back. 65.165 degrees. Okay. And keep in mind that we do want to round this to the nearest tenth. Okay. So this is going to give us a value of 65.2 degrees. Okay. Keep in mind that that value, 65.2, that's giving you an answer in quadrant 1. So how do we find quadrant 4? Right? So quadrant 4, if we go all the way around then, we know that if this angle right here, let me do this in different colors so it's more noticeable. If we know that this angle, this reference angle of 65.2 degrees takes us to quadrant 1, then we also know symmetrically we have a reference angle down here of 65.2 degrees as well. So in turn, what we can do is to find our true angle, then we can take a full circle and subtract that 65.2 degrees. So we can see that theta is about equal to 360 degrees, a full circle, and take away the reference angle of 65.2 degrees, and that'll give us about 294.8 degrees. Okay, and so you can see here, based on the diagram, doesn't match up. Well, 65.2, that is a little shy of 90 degrees, right? 65.2. And also 294.8 also takes us a little bit past 270 degrees as well. So it looks like that graphically we have verified that what we found algebraically here. Okay. Take a look at example 2. Graph cosecant of theta is equal to 14. Okay, well, what have we learned about cosecant? We know that cosecant is really the same thing as the reciprocal function of sine. So what we're really saying is 1 over sine theta is equal to 14. Or In turn, what we can also think of this as is if we just kind of multiply things around, right, doing a little bit of algebraic manipulation here, what we're saying is that sine of theta is equal to 1 over 14. Okay? Let's pause there. Okay, I just wanted to show you what exactly cosecant was talking about. But before we get there, let's actually look at this graphically. Now what we're dealing with here is a cosecant function. If you recall, cosecant, because it's the inverse of sine, you think about what sine looks like, and sine looks like this. Remember how we drew it before? It's a dotted line, and then we create the asymptotes where the x-intercepts occur, just like this, like that. And then remember that the true cosecant graph occurs as a reflection, or rather up above those dotted lines. So this is actually going to represent our cosecant graph here. Okay, and oh yeah, I also forgot to do the other side, didn't I? So keep in mind it goes down this way, and then you have asymptotes here. Oops, that's a little lighter. Okay, just like that. All right, so that's going to be our cosecant graph. Now, if you think about what this represents again, remember it's really like a system of equations. One where cosecant theta is equal to y, and also where y is equal to 14. Oh, 14, that's really high, isn't it? Since this is a value of 1, our normal sine graph, 14 takes us like way up here. Just imagine that's 14 there. Okay, and what we're trying to find is when it intersects this particular horizontal line. And we see that occurs at these locations here. Okay, remember that we're only contained within 0 to 2 pi, so really I didn't need to draw this part right here. So it looks like we're going to have two intersection points in this particular problem here. And so let's actually verify that algebraically. Let's find that value. Okay, so currently what we have is sine of theta is equal to 1 over 14. Remember, visualize this. What does this mean? You've got your trig function isolated. So think A, S, T, C. When does sine give you a positive value? That's going to be in quadrant 2 and also in quadrant 1. So let's go ahead and find that value. If we do the arc sine on both sides, just like that, those cancel. Theta is equal to sine inverse of 1 over 14. That's going to give us a value of 4.09. Oh, wait, that's in degree format. Let me go in radian format here. That's going to be a value of 0.0714. Okay, let me write that down. 0.07148. Okay, so that's going to be a value of 0.07148, blah, blah, blah. We want to round this to the nearest tenth, so we're talking about a value of about 0.1 then. Okay? Excuse me. So that's going to be in, as I draw this on my unit circle, that's going to be a value in quadrant 1. But remember, we want to find the value in quadrant 2 as well. So if my reference angle was 0.07148, then keep in mind that this also has a reference angle of 0.07148. So how do we find the answer in quadrant 2? Well, remember that this is the true angle we want right there. How are we going to get that amount? We need to take a full semicircle and backtrack our reference angle that we know. So the other value we need is the value of a full semicircle, which is pi, and we're going to subtract that value of 0.07148. Okay, and that's going to give us a value of, let's go ahead and do that in our calculator. Enter, and we'll do pi minus answer, and that'll give us a value of 3.0701. 3.0701. Okay, so 3.0701, which again rounded to the nearest tenth, we're looking at an answer of 3.1. So our two answers that we get for this problem are 0.1 and 3.1. Verifying that graphically, look at that. We know that the cosecant graph, it is going to be really, really close to that y-axis, and that's the value of 0.1. And it's also going to be really, really close to that value along the asymptote. We know that asymptote is at pi, which is about 3.14, and we're getting a value pretty close to that, which is 3.1. So we have verified that graphically as well. It looks pretty darn close.